Hello everyone, and today we're going to be talking about controls. So I prepared this lecture in collaboration with one of my friends, Kyle Stakowitz, and he was on RoboCup for a while, and he's still around, and he knows a lot more about controls than I do, so hopefully we'll learn something there. So to start off with, what is a control system? So it's kind of simple at first. So essentially you have some sort of input, you have some sort of system, and you have some sort of output. So we can think of this as our input is some state vector x, and our output is some control vector u. And it can be applied to a lot of different systems. So I do my research in controls, and one of the things I work on is autonomous cars. So we can use this system for autonomous cars, we can use it for moon landings, we can use it for controlling an HVAC system. There's kind of limitless possibilities. So the system we're going to be using for this week is the same system we've been using for a while. This is our robot, so it's going to be a differential drive robot here. And what that means is that I have two wheels, and each one is controlled independently. So this system has limitations. There's no way for us to move the system this direction because of where our wheels are located. We have to move in line with the wheels. So if we want to spin, we have to put one going forward and one going backwards in order to rotate in place. If we give one wheel a faster speed, the other one a slower speed, we slowly drift in an angle. But this will be a constant curvature, assuming these two velocities remain the same. So the first thing we're going to be talking about is open loop control. So this is a paradigm where you calculate the control signal that you expect to make the system do what you want. So for example, with our differential drive robot, let's say I'm in some position here, and I want to get to some goal over here. So what you would do is generate some path with some curvature that would get you to your goal. Now this is really nice. I can calculate exactly what this u would be. Since I move at a constant curvature, I can figure out what that curvature is, and I can just match that u control. And assuming everything's perfect, what I'll do is I'll drive from one point to the other. Now, this is great. We have a problem. The same problem we have in pretty much every lecture that I've talked about, but noise. There is noise. Remember that we have some nominal dynamics here, we have some control here, but we have this WT, and this is a stochastic random variable that induces noise into the system. If I were to do that, if I were to have my robot here, trying to get to some goal over here, and I apply this constant curvature, what I would actually get is some path that looks more like this, where I drift off. And depending on the realization of my stochastic noise, I'll tend to get different trajectories. And this is just because of that propagation of the stochastic noise. It builds up over time, and we're never going to quite reach the goal. So how can we handle this? How can we solve this stochastic problem? Kind of the idea of controllers. And we're going to get our state from some sensor, like here would be an encoder for our wheel velocities. And then we're going to use this velocity measurement to change our control. So what we were doing before in the open loop sense is we were just computing some control, and then our robot was effectively blind, and we would just drive forward, assuming that our control was right. So now what we're going to do, based on some sensor readings I'm getting from the system, I can modify my controls so that I match what I'm trying to do. So the first such controller that does this is called the bang bang controller. So when the state is less than the target, give it some u max, and when the state is greater than the target, give it some u min. So the way to usually think about this is that we are on a flat line, we have some cart here, and then we have some target position here. We want to move this cart so that it's right there. So our max control is going to move us this direction, and our min control would move us backward. So what the bang bang controller would do is apply the maximum control to accelerate us this way until it reached this goal point, and then it would apply the minimum control. But depending on our dynamics, you'll get something that looks more like this, where you'll drift back and forth slowly until you eventually converge. So the state plot of that would look like this. So let's say this is the target position that we want to reach. And with a bang bang controller, what you'll tend to see is something that looks like this. You're going to oscillate and slowly slow down over time. And this technically works, but we get really jerky controls. Think of like you're driving in a car, and the only thing the person can do is hit the gas at full speed or hit the brakes at full speed, and nothing in between. You'll technically get there eventually, but it's going to be a very bumpy ride for a while. So we don't want this. So what can we do? Can we do something better? Can we use the intuition that our error is changing over time? The control I want to apply here and here are very different. Here, I'm pretty far away, and I have a long way to go, so it's okay to use a high control. But here, I'm pretty close to my set point. What I want to do is back off the control a little bit. So this is like when you're going down the highway and you're sitting at 65 and you're trying to go to 70. You don't floor it, you lightly tap on it. But if you're just merging onto the highway, you're going to floor it a lot more. So that's what we call proportional control. Proportional control gives the control input relative to the error plus some feed-forward turn. So this is that control that we talked about earlier in the open loop sense, where you just completely closed your eyes and drove forward. Our error here is based on the deviation of our current state from some target set point, so our target state, just like we talked about earlier with that cart. So now we have some constant Kp times our error value plus our feed-forward control. So what you'll tend to see with a P controller is one of two things. So if we draw our state plot here, and we have some target position here, the example we're going to be thinking about is trying to match some velocity. So let's say we have some car, and we're trying to go 70 miles per hour, starting from rest, and we'll be doing this up a hill. So if you let off the gas, you'll decelerate, so you need to apply some constant pressure in order to get us up the hill. So if we use our feed-forward control, what that'll tend to do is we'll accelerate, we'll decelerate a little bit, and we'll kind of oscillate, but we'll eventually converge to some flat point. Now this is good, but we're not getting to our desired speed. So now if we apply our Kp controller, and we leave Kp is large, we'll tend to oscillate around the set point. So we'll go up really fast, and we'll oscillate back and forth, and you kind of see this behavior, which may eventually dampen out, and it may not. Now if Kp is small, then we'll see something that looks just like the feed-forward example, except we'll converge to a point that is closer to the set point than we had before, but it won't actually reach that set point, because as x approaches r, so we get closer to our target speed, our error approaches 0, and then p here is doing nothing. So eventually converge to some point where e is just high enough to enable p, but not high enough to actually reach the set point. So how can we handle this? The error that we see here is this thing called a steady state error, because it's pretty steady over time. So there's some way we can compensate for this. And that's what we're going to do in the integral controller. So we'll have the exact same example we had before of trying to drive up that hill at a constant speed, and we'll have some Kp, and now we have this Ki, which is based on the summation of this error term, and still have our feed-forward control. So if we look at the state plot with some target position, what we'll see with a Ki term is that if we have a low p like we had before, we will converge up to our steady state error, but since we have this I continuing to push us up, we should actually go and reach the set point. But this I will also tend to make us overshoot, because if you think about it, I is building up this entire time. So this value is getting increasingly larger and larger. And it's not until we go over the set point in green that we actually start decreasing this value. So we tend to overshoot and then oscillate back and forth. How can we compensate for this oscillation? We can do this using a derivative term. So if we add a term that includes the deviation of error, we have this Kd term, which is based on our derivative of our error, a Ki term based on our integral, and a Kp term based on our proportional term. What we get is the PID algorithm. So this has a proportional term, an integral term, and a derivative term, plus our feed-forward control. Now, using this, what we can do is run the PID algorithm. So what the derivative term will do is it'll damp out those oscillations. So if we're doing the exact same thing we had before, which had a car going up a hill trying to reach 70 miles an hour, this is our target set point. So when you're tuning PID, what you'll want to see is some proportional term such that you overshoot a little bit or get very close to your set point, some d so that your peaks are not too high, and then some integral such that your steady state error is very close to 0. Now, balancing these three terms can be very difficult and often just comes down to the application that you're doing. So in summary, during this lecture, we talked about how the objective of controls is to drive the system to a given state, that we have things like the bang-bang controller that are very aggressive. We can use PID controllers to balance out some of the difficulties with the bang-bang, but potentially hard to tune. Getting those P, I, and D values exactly is hard, and a lot of that it just depends on the system. Now, there are a lot of hacks to make PID work better that we're not going to be talking about, but I really encourage you to look up this algorithm if you're interested in it.